Okay, we'll see. Okay, so far we have seen in the first part of the course the crystal structures. So what was related to the geometrical arrangement of the nuclei and the properties of the various crystalline structure, the classification in Bravais lattices, and we have seen the reciprocal lattice. Now we are going to start the part on the electronic state in the crystal. So what are the properties of the electronic state in such a periodic arrangement? So this is electronic states in crystals. Alright, so what we are considering is periodic potential, and we want the electronic levels, the electron levels in a periodic potential. So the potential we are considering is the crystal potential V of R, and this potential must have the periodicity of the Bravais lattice corresponding to the crystal that we are considering. So V of R is equal to V of R plus capital R, where capital R is a vector from my Bravais lattice, and this must be true for any vector R belonging to the Bravais lattice of my crystal. So this is the property that I impose on my potential. It must have the periodicity, the full periodicity of the Bravais lattice of my crystal. So I consider a periodic arrangement of nuclei. Here I consider that they are just on, it's a simple Bravais lattice, and on each point of the Bravais lattice I consider that I have a nucleus. So, okay, we have periodic arrangement of nuclei, and the corresponding potential induced by the nuclei has this periodicity. So now if I consider a line, I take my axis going through one of these row of nuclei, and I sketch the potential that is obtained by superposition, let's say, of the potential induced by each of my nucleus. I will obtain qualitatively something of that type. So I'm cutting the potential here, V of R. This is my axis. So this axis, and I have the position here. Let's see, of my nuclei, and here, this is my direction, and I will have for each of this position of the ion, a potential of the type Z, where Z is the atomic number, E squared over R minus capital R, where capital R is one of my Bravais lattice vectors. I positioned the ion on each of these points of my Bravais lattice. For simplicity, I consider a monoatomic lattice, that is with one type of atom on each of the points of my Bravais lattice. So around each of these points, I'm going to have Coulomb potential induced by the nuclear charges, and so the potentials will diverge at the position of the nucleus, and if I superpose, I guess I can obtain something of the type with a divergence at each of the position of the nuclei. So this is, let's say, the superposition of the atomic potential, the potential induced by each of the nucleus. It has, of course, the periodicity of the Bravais lattice. And so this is, let's say, the bare potential. Now, if, since I have in my crystal also electrons, I can expect that because of this strongly attractive potential at the position of each of the nucleus, the electronic charge or the electrons are going to concentrate in this region. These are the regions that are the attractive regions, so one expects the electrons to concentrate in the most favorable region, and the electronic charge that will correspond to this distribution of electrons that want to be around here is going to give a potential that will reduce the strength of this attractive potential, because the electronic charge will induce a potential that is repulsive for the other electrons. So one can expect that with the electron-electron interaction, the resulting potential, the total potential, will be reduced in those regions, because the electrons are going to accumulate there and reduce this potential due to the nuclei. So one can expect maybe a potential like this. Of course, because of the periodic arrangement of the nuclei, the electronic charge will have also a periodic arrangement, and the resulting potential will have the same periodicity. So one expects a potential that will reduce the strong attractive amplitude here near the nuclei, but it will be a potential that will still have the periodicity of my Bravais lattice, of course. Okay, so this is what one may expect with the electron and electron interaction, the potential in that total potential that the Mill field potential that the electron will feel in the crystal. So this, as I mentioned at the beginning of the course, I'm in the framework of the independent electron approximation. Electron approximation. And what I'm going to solve in this course is the Schrodinger equation for one electron. That is the one electron Schrodinger equation, Hc of R is equal to my Hamiltonian with the kinetic part, so minus h bar square gradient square divided by 2 times the electronic mass plus my potential, my crystal potential, which will be this potential in red. I'm in a mean field approximation, 1 electron mean field approximation, so this is equal to epsilon, the eigenvalue C of R. So I will solve one electron Schrodinger equation with the crystal potential, which has the periodicity of the Bravell lattice of my crystal. Okay, I forgot the C here, and not enough space. Okay, so this is Hc, sorry, R is equal to epsilon C of R. Okay, alright, so this time let's go. In the next semester, you will see in the electronic structure course density functional theory, which is a theory that is used based on the theorem where instead of solving the many-body Schrodinger equation, one simplifies and considers that the variable, the density of the electrons can be used as a variable that will determine the ground state of the system. And with this approach, within density functional theory, one can make an approximation that the potential will depend only on the charge density locally. That is, the potential in this theory will be determined just by the charge density in the crystal. So in density functional theory, and this you will see in the next semester, so density functional theory, this is a general theory, but one can make an approximation which is the local density approximation. And in this context, the potential, one can actually write it this way. So the potential in my crystal will be the potential generated, the Coulomb potential generated by the nuclei charge. So Z, the atomic charge, Zi, let's see, is square. Well, I have a monoatomic crystal, so in this case it's just Z. R minus R I. So this is the Coulomb potential generated by the nuclei charge. And then the part related to the electron will be just the electrostatic potential generated by the charge density of my electrons. So I integrate over the R prime E square times this charge density of the electron, rho of R prime, divided by R minus R prime. So this is just the potential induced by the electronic charge rho of R minus R prime, and it's divided by R, so it's the potential at R induced by my electronic charge density rho of R prime. So this is the second term, which we call also the Hartree term. And then in the local density approximation, the remaining part that includes everything that has not been put in this electrostatic part is called the exchange correlation potential, Vxc, and it depends on this electronic charge V of R prime locally. Sorry, V of R, not V of R prime. So the local approximation is this potential V of R depends on the charge density locally, that is rho at the point R. The most general potential that would not be within the local density approximation would be a potential where rho at the position R depends on the charge density at any other R, so R prime. So in general, we would have here rho of R prime, and we would have an integral that would, so the potential at R would depend in the most general way on the charge density also at the other point R prime. And the local density approximation is that it just depends on the charge density at the position R. Okay, so in the local density approximation, which is widely used to do band structure calculation and electronic structure calculation, this is the form of the potential in the crystal. So it has the potential induced by the nuclei, the electrostatic potential induced by the electron charge density, and this additional term, which is the exchange correlation potential, and these there are forms of this potential that have been proposed and that are very accurate, allowing to do electronic structure calculation. So, okay, so this is just to show you in practice which form this potential has, but for what we will discuss in the following, the important is just that it has the periodicity of the Bravais lattice. And of course, this has the periodicity of the Bravais lattice. This is obvious. This is also obvious because the charge density has the periodicity of the Bravais lattice, and also this will have the periodicity of the Bravais lattice because my charge density has this periodicity. The electronic charge density has this periodicity. Okay, and in here, the Ri are the position of the nuclei. nuclear. Okay, so in general, in electronic structure calculation, one makes another approximation. So one was this local density approximation, and the other one, which is often done, is that the electrons in a crystal, we can put them in two different categories. The one that are essentially the core electrons, the one which are the most bound, those electrons, typically one can make an approximation assuming they will be just like in the atom. They are so tightly bound that basically they remain as in the atom, and one will consider in what one will solve, the Schrodinger equation one will solve just the valence electron, because those are going to be somewhat modified. They will function with respect to what they are in the atoms, and those are the ones that will make the chemical bonds, the valence electrons. So often, in practice, one will solve just for the valence electrons, and the justification is that the core electrons have energies that are so deep, they are so tightly bound that basically their energy scale is orders of magnitude different from those from the valence electron. So in practice, the core electrons are so tightly bound with energy, binding energies much larger in magnitude than those of the valence electron. And that one, that they remain basically like in the atom. Sorry. Typically, the core electrons have binding energy of the order of 50 eV, which is huge. The valence electron, typically it's 1 eV, of the order of 1 EV. So the core electrons are just assumed to be like, with energy like in the atom. So one solves for the valence electron, which are the important ones that make the chemical bond in the crystal. So the potential that one will have in this case, V will be a sum over I, but here we will have the potential of the ion or the atoms of the atom, and we call it a pseudo potential. That is the overall potential that is created by the nucleus and the core electron on the valence electron. So this also depends on R minus I, the position of the atom. And then one has the Hartree potential, electrostatic potential generated by the electronic valence charge density. So this is valence of R minus R prime. And one has the exchange correlation potential, but just due to the valence charge density. So typically this is what one will solve. So only for the valence electron with this potential, where here one has the electronic charge density corresponding to the valence electron. And this potential here is an atomic pseudo potential. Sorry. Okay. And it corresponds to an ionic charge or ion charge. Which is just the atomic charge minus the number of core electrons. Times the electronic charge. Well, just to be a little bit more explicit, if you consider, for instance, that the core charge rho prime is equal to a sum over the nuclei of n core delta R prime minus Ri. So if I consider that in my crystal the electrons are tightly bound to the nucleus and are so localized that I can approximate them, the charge distribution by delta function. So with on each at each position in my lattice the number of core electrons. Then if I use this and I put it here, what I will obtain when I integrate over R prime is just the number of core electrons times E squared divided by R minus capital R, the position of the ion, and what I'm obtaining for this potential is just here Z minus the number of core electrons divided by R minus Ri. So basically in the limit where my electrons are so localized that their charge density can be approximated by a delta function, this potential is just the Coulomb potential corresponding to a charge that is the atomic number minus the number of core electrons times the electronic charge. So in the limit of tightly bound core electrons, this is just the Coulomb potential rescaled that corresponds to the ion, basically. And then one can separate also because there will be no overlap between core charge and valence charge, and one can separate also this and obtain just the exchange correlation potential that depends explicitly only on the valence charge. Okay, so this is the approximation that we will make in general, that is, we solve just for an effective equation with a potential that acts just on the valence electron. We solve just for the valence electron. Okay, in any case, what I'm going to tell you now doesn't depend on whether one makes this approximation or not, core electrons in the valence or not. The theorem that we will use, the Bloch theorem, just considers a periodic potential. So this has to have the periodicity of the Bravais lattice. So Bloch theorem is what I'm going to discuss now. So the Bloch theorem, which many of you already saw, states that the solution the solutions of the Schrodinger equation Hc is equal to epsilon psi with H, the Hamiltonian being H bar square, so the kinetic part, plus V of R, the potential, with V of R being periodic. So I can write explicitly this periodicity, that is V of R plus capital R is equal to V of R for any R belonging to my Bravais lattice. So the solution of this Schrodinger equation with a periodic, an Hamiltonian with a periodic potential, and by periodic I mean having the full periodicity of the Bravais lattice, then this solution can be, according to the theorem, can be written in the form C of R is equal to epsilon I K R times U of R, where U is a periodic function. And here I can label this with a K. So this my solution can always be written in this form. With U having the periodicity of the Bravais lattice. So where UK of R is periodic, that is K of R is equal, UK of R plus capital R is equal to UK of R. So the Bloch theorem states that the solution of my crystal Hamiltonian, since I consider a crystal potential that has the periodicity of the Bravais lattice, can always be written in this form, that is an exponential IKR, where K is a real vector with real numbers, and have a function U of R that is periodic, that has the periodicity of the Bravais lattice. So this is the Bloch theorem. Now, question. Does this mean that this function has the periodicity of the Bravais lattice?
The phase factor.
Yes or no, in general? R is a vector. Any real vector? Is it periodic or not?
It is.
The question is, does it have the periodicity of the Bravais lattice? By periodic I mean periodicity of the Bravais lattice. Because, the Hamiltonian has the periodicity of the Bravais lattice. Okay? This is what I state here. Does the solution have the periodicity of the Bravais lattice or not in general? No. This has the periodicity of the Bravais lattice, but if I take an arbitrary K, as we have seen, the wave functions have the full periodicity of the Bravais lattice only in some specific case, when the G are vector of the reciprocal lattice. These are the only plane waves that give the full periodicity of the Bravais lattice. But in general, a K that would be smaller than the first G vector, that would have a smaller norm, would give a plane wave that would have a different periodicity than the Bravais lattice. The periodicity would be 2 pi over K, the norm of K, and it can be different from the it will be different from the periodicity of the Bravais lattice. So, in general, except for instance for K equal to 0, which is a reciprocal lattice vector, or for G, K equal to G, that would be a vector belonging to the reciprocal Bravais lattice. This does not have the periodicity of the crystal. So you have a situation where the Hamiltonian has a given periodicity of the Bravais lattice, but not the solution. Does it make sense? Did you see other example of this type in your previous studies? That is, the solution don't have the full symmetry, because periodicity is a symmetry operation. So did you see some example where you had an Hamiltonian, very symmetric, with some very symmetric property, and the solutions don't have the symmetry of the Hamiltonian? Does it... for instance, let's consider the hydrogen atom. What kind
like some wave functions didn't have the whole circle symmetry.
Yes. Actually, let's consider the simplest operation, that is inversion symmetry. Because, of course, the Coulomb potential of the hydrogen atom, the potential has the inversion symmetry. R going to minus R gives the same potential. Now, do the eigenstate, the hydrogen state, have all inversion symmetry? So, the S state, yes. And then, the next states, for instance, the P states, do they have, if you have a P state, which transform, let's say, like X. If you apply the inversion symmetry to L equal 1 state, the PX state, for instance, well, it goes to minus itself. If you calculate Px of minus R, you will have minus times minus Px of R. So actually it's antisymmetric, the P states. So it doesn't have the symmetry of the initial Hamiltonian. You have even and odd states, and the Hamiltonian or the crystal potential is even. So this also is an example where the eigenstates don't have the full symmetry of the potential. And actually what you find in the hydrogen atoms is that you can separate into even and odd states. And the even and odd states are the eigenstate of the inversion symmetry. That is, they transform either into themselves or into minus themselves with the eigenvalue 1 or minus 1. And the inversion symmetry commutes with the Hamiltonian, and therefore you can simultaneously find eigenstate of the inversion symmetry and of the hydrogen atom Hamiltonian. Here it's the same. That is, we will see it's the same because actually the Bloch state are the eigenstate of the translational symmetry operator. So they commute with the Hamiltonian, and one can simultaneously find eigenstate of the translational operation symmetry with the Bravais lattice and of the Hamiltonian. So the Bloch states actually are just the eigenstate of the translational symmetry operation with the Bravais lattice. So the Bloch theorem, this is just stating this is just stating that the eigenstates of H of the Hamiltonian, crystal Hamiltonian can be chosen to be simultaneous eigenstates of the translational operator the translational operator T of R for any R belonging to the Bravais lattice of the crystal. So the Bloch states are the eigenvectors, eigenstates of the translation operators for any vector R translation that belongs to the Bravais lattice of the crystal. So one can show this, that is, if I apply the translation R to a Bloch state, CQ of R, by definition the operator TR is changing CK of R into CK of R plus capital R. This is my definition of the action of this operator on any wave function. And if I use here Bloch state, that is having this form, then I obtain exponential ik times R plus capital R here times uk of R plus capital R. Okay, this is just applying this on a Bloch state here, and here I'm going to obtain exponential ik, and I use first this term, capital R, times exponential ik small r times uk of R plus capital R, but my uk of R are periodic states, so uk of R plus capital R is equal to uk of R. Okay? And this is just my initial Bloch state, ck of R. And this is just a constant phase, because R is just a vector of the Bravais lattice, and this is the constant phase. So indeed, my ck of R, my Bloch state, are eigenstate of the translational operation with this as eigenvalue, which can be labeled with this vector k, which is therefore a quantum number, a good quantum number. So, and this is valid for any R belonging to the Bravais lattice. So, my Bloch state, the Bloch state are just eigenstate of the translation operator for the Bravais lattice. Translation of the Bravais lattice. So this is an eigenvalue. Of the translation operator for any R belonging to my Bravais lattice, and the corresponding eigenvalue and this corresponds the corresponding eigenvalue has is a quantum number, has a quantum number corresponding to k. So corresponding to the quantum number k. So for each, that's why I labeled my Bloch state with this k, the momentum, because it's a quantum number that is related to the eigenstate of the translation operation for the Bravais lattice. So k is a good quantum number, and I can label my state, my eigenstate of the Hamiltonian using this quantum number. That is, I can work at in a given subspace corresponding to a given k. I can separate the eigenstates using this k. So there is a second form of Bloch theorem that one also uses often, and which just states that is that the Bloch state are the eigenstates of the translation operator with this eigenvalue. So the second form of Bloch's theorem is just that psi of k, the Bloch state, when one translates it, so psi of k of R plus capital R is equal to the Bloch state psi k of R times exponential I k R, capital R. So this form just states that when I apply the translation operation on pk, that is pk of R plus capital R, I just obtain the Bloch state. So it's an eigenstate of the translation operation with as eigenvalue exponential ikr, which is this. So this is just stating that the Bloch states are eigenstate of the translation operation. This is the second form of Bloch's theorem. One this equation is just the second form of Bloch's theorem, the second way of introducing Bloch states. And so this is valid, of course, for any vector R belonging to the Bravais lattice. So this is the second form of Bloch's theorem. The first one is C of Ck of R is equal to exponential IKR, small r, Ck, Uk of R. So there are two forms which are equivalent. Okay? So I didn't prove formally Bloch's theorem. You can find the proof in textbook, but basically it's very natural in the sense it just results for it a consequence from the fact that the Hamiltonian commutes with all translational operator corresponding to translation where the vector are vector of the Bravais lattice. So the Hamiltonian commutes with this translation operator, and the eigenstate of the Hamiltonian can therefore be written, can be simultaneous eigenstate of the translation operator. Okay, so this is Bloch theorem, and now I would like to give you two consequences of this theorem that we will use. So, here. So, let me just give some consequences. And the first one is actually that one can always write a Bloch state as a Bloch state with k vector in the Brillouin zone. So if I write my Bloch state Pk of, I write my Bloch state as exponential I k times R Uk of R. I can always, for any k in space, so this is my reciprocal lattice. Simple cubic lattice, square lattice. So this is in reciprocal space, and let's say I have a k vector that is outside the Brillouin zone. So this is my k vector. I can always write it as the closest g vector. So this is my g vector plus a vector k that is inside the Brillouin zone. So my vector here let's say in red, belongs to the Brillouin zone. So I can always write my K as a K inside the Brillouin zone plus a reciprocal lattice vector, and this is the vector inside the Brillouin zone. So here I can always write my Bloch state with K outside anywhere in space, outside the first Brillouin zone, as exponential I K inside the Brillouin zone times R times exponential I J R UK of R. So this was with K outside the Brillouin zone. With K outside the Brillouin zone. And this is therefore something that is periodic. This exponential IJR UK of R is a periodic function. We have seen that the reciprocal lattice vectors are the vector that makes this function having the full periodicity of the Bravais lattice previously. So this is periodic, and therefore I can always write my Bloch state as exponential I K R with K inside the Brillouin zone times a periodic function. So I can always write it, the crystal state as Bloch state with K inside the Brillouin zone. Is it clear? The Bloch state only states that the states, the eigenstate of the crystal, can be written as this kind of phase time a periodic function, and I can always do it with a K inside the Brillouin zone. I can always rewrite it in the form of a Bloch state with K inside the Brillouin zone. Alright, this is just what a consequence of Bloch's theorem. Now, another consequence this takes a little bit more. Okay, so just to restate it, so Bloch theorem, this is just the previous one, so can always be restated as, okay, when I have a Hamiltonian of that type, with this potential being periodic, and I mean with the periodicity of the Bravais lattice. Find the solution. The solutions can always be written as Psi of R is equal to exponential I k R u k of R with k belonging to the Brillouin zone. So, okay, so this is just the consequence. Alright, so now we will use that. This is already something that simplifies tremendously the problem, because now we can just work at a fixed k, so we can just choose a k, and the solution that we are looking for is just a function that is in the unit cell. That is, it's periodic, so it's enough to know it in the unit cell. So from the solution in general of the Hamiltonian, the crystal Hamiltonian, we have simplified it into solution that we can classify, so by a given quantum number, k, so we can separate in subspaces with a given k, and in addition this k we can restrict it inside the Brillouin zone without losing any generality. And what we need to find, the only thing we need to find, is a solution inside the unit cell with periodic boundary conditions. So we have simplified quite a bit already the problem, and now we are going to derive an equation to find this this function inside the unit cell. So we start from the general crystal solution. H psi is equal to epsilon psi, and we are writing our psi as exponential I k R u of R. So now we want an equation for the u of R is equal to epsilon I k R u of R. And we know that our Hamiltonian here includes second order derivatives, so we have the Hamiltonian that is gradient squared over 2m. So we have to derive twice a product of two wave functions. And then we have V of R, and that's simple, it's just a scalar, so that will be easy, but we have to work a little bit to act with this second derivative on the product of the two wave functions. So for this second order derivative gradient, if I apply this to a product of two wave functions, this gives me just the second order derivative on f times j plus 2 times the gradient of f times the gradient of J plus f, and I apply twice the gradient on J. Okay, so this is just deriving twice. And now I need to apply this on my specific wave functions here. So if I apply gradient square on exponential I k r u, I'm going to obtain I have to derive twice the exponential here, and then I have 2 times the gradient of exponential ikr times the gradient of u plus exponential ikr and the gradient square u. Okay, so this is what I have to evaluate. Alright, so that's easy. When I apply this, I just obtain minus k square, and I have again my exponential here. It's an eigenstate of the derivative. U plus 2 times, so if I derive here, I obtain ik, so ik times exponential ikr times the gradient of u, and the last term is just the exponential times the gradient square of u. Okay? So it's nice because I reobtain my exponential in all cases. Now I'm going to use the full Hamiltonian. So the equation I have to solve is this one. So minus h bar square gradient square over 2m plus v of r exponential I k r u is equal to epsilon exponential I k r u. So I have already worked this out here. So I'm getting minus h bar square over 2m, and then on what I have here, so minus k square exponential I k r u plus 2 I k exponential I k r gradient of u plus exponential I k r the the second derivative of u, gradient square u. So this is the first term. Then I have my v of r, exponential I k r u is equal to epsilon e I k r. Okay? Alright, so, well, that's very nice with exponential because one recovers them everywhere and one can simplify. So I can write here like this, and I'm obtaining an equation just for u, which is what I wanted. I wanted to solve for u. So what I'm obtaining, if I rearrange a little bit, is so h bar square over 2m gradient of square plus 2i k times gradient minus k square u is equal plus v of r u is equal to epsilon u. Okay? And if I want, I can also rewrite this as minus h bar square over 2m gradient plus I k square plus e of r u is equal to epsilon u. Okay? And I can call this an h of k, if I like. So I will call this h of k, and I will have h of k u is equal to epsilon u. So I have eigenstate problem. So with h, it's not the initial Hamiltonian, it contains two additional terms here, but it is a second or a second order differential operator that has the nice property of being Hermitian. If you take the complex conjugate, you obtain the H plus. I mean, it's Hermitian. And the solution, as I mentioned, the U, we just have to look for a function inside the unit cell because U is periodic. So we just have to look for a solution U inside the unit cell with periodic boundary condition, and we have just to look for solution at a given or for each k. For each k point inside the Brillouin zone, in the Brillouin zone. So for a fixed k that we choose inside the Brillouin zone, we should solve this inside the unit cell with periodic boundary condition. Okay? So this has some interesting consequence, because solve such condition that is solving for a Hermitian operator with states inside the unit cell that have periodic boundary condition has actually, one can prove that this gives rise to a discrete spectrum. If one solves in a finite volume, in a box, this kind of second order operator, Hermitian operator, this gives rise to a discrete spectrum, like normal boundary condition will give you, on the border of the cell, will give you a discrete spectrum. The same applies for periodic boundary condition. It's like when you solve inside the box, let's say with infinite wall, you are going to obtain a discrete spectrum inside your finite volume.
Sorry.
So, yes?
No, but why is the K acting as a, in the last Schrodinger equation, why is K acting as a gauge field? Because
it's a good quantum number. It's a fixed, what do you mean?
Yes, but for example, if we have a Schrodinger equation in electromagnetic field,
it's not, I just call it this way. The only property I can tell you it has is that it's a second order differential operator that is Hermitian. This is all I state. Okay, we derive it as this form, and that's all. But this is enough, actually, to have as a consequence that the spectrum inside the box, that is, I have to solve for my function u inside a finite volume with periodic boundary condition. And either periodic or normal boundary condition that is imposing it goes to zero, for instance. So normal boundary condition means it goes to zero, like infinite wall. When you probably saw the solution, a quantum well with infinite wall, you get a discrete spectrum. Here it's the same with normal boundary condition, and this type of operator you get a discrete spectrum. So I'm giving you this as a statement, but this can be proven. So as a consequence, so now we have an equation just for you, and we just have to find the u of our inside a finite volume, which is the unit cell, with periodic boundary condition. And this gives rise to a discrete spectrum. So we are going to find or obtain eigenstates. So we start, k is a good quantum number, so we can use it. And then we will have eigenvalue number 1, 2, 3, which I can index with this N. It's a discrete spectrum. For any K, I will have a series of eigenvalue that I can label with N, and U and K is the corresponding eigenstate. So I will have in my box this solution corresponding to a discrete spectrum, and one can also show that the UN, if I take all the states that are eigenstates, will form a complete basis. Okay. Now I will just finish because this directly leads to now band structures. Now, if I look just at the one-dimensional case, so I'm just looking at the what this implies in one dimension. So in one dimension, I have just the periodicity characterized by my length A. So my reciprocal lattices are just R equal NA, where N is an integer, and my reciprocal number, it's not vector, my G are just M times 2 pi over A, where M are integers. So if I'm looking along the k-axis, so in my reciprocal space, this is the origin. I have my first G vector that corresponds to 2 pi over A. And then I have the next one here, and I have here minus 2 pi over A. So this is along my axis the reciprocal points. And I know that it's enough to concentrate inside the Brillouin zone to have the full spectrum of my eigenvalue in the crystal. So I will concentrate just on the Brillouin zone here and choose K inside the Brillouin zone. So I will choose a K here, and I know that I'm going to get a discrete spectrum, so it has to start with one value, which is the lowest energy value here. So this is my energy 1, n equal to 1, and then I will have an n equal to 2 here, 3, and so on. So for this given k, I'm getting a discrete spectrum, epsilon 1, epsilon 2, epsilon 3 for this k, which are solution of hk u is equal to epsilon u. So I can put my index n here and k. So these are the epsilon for this k 1, 2, 3, and so on. Now, if I choose a K prime that is arbitrarily close to this K, my energy epsilon of K prime will be asymptotically close to the epsilon of K, because my H is analytical in K. It's an analytical function of K. So I can expect that when K becomes closer and closer, K prime closer and closer to K, my energy epsilon of K prime will asymptotically tend to the value here. So I will have another spectrum here, but I know that the energy are going to be very close because they have to merge when K goes to K prime goes to K. So basically, if I continue for various K, I'm going to obtain a function epsilon here of K that has to be continuous. So I'm going to obtain some epsilon n of K, which gives me a band, which we'll call a band. And the ensemble of this epsilon n of K is going to be what we call a band structure. Oops. Okay? Is
it nature?
Excuse me?
Is it nature something?
No, I think it's in the next. Yeah, I think so. Okay. Now there are two properties. I'm going to finish here, that I want to give you concerning band structure. The first one is that the band structure is periodic. So the first property of the band structure is that the band structure is periodic in reciprocal space. That is, if you take a K outside the Brillouin zone, an eigenstate outside the Brillouin zone, we know that it can be rewritten as an eigenstate inside the Brillouin zone. Of course, and since it's the same state, it will have the same energy. So basically, the band structure, and we know that we obtain the full spectrum inside the Brillouin zone. So there is a one-to-one correspondence. Any state, eigenstate outside the Brillouin zone can be written as an eigenstate inside the Brillouin zone, from what we have seen. Obviously, it has the same eigenvalue. So basically, we have periodicity in reciprocal space with translation of the G vectors. So this is one of the consequences, periodicity. And the second consequence, or the property, is that epsilon of minus K is equal to epsilon of k. So it's symmetric, which I try to draw here for k and minus k. And the reason is that if I apply h of k on my eigenstate, u of k, my solution, and if I take the complex conjugate of this equation, I'm going to get h of k star, the complex conjugate, uk complex conjugate epsilon k, well, before without vector, it's valid in 3 dimensions also. Now, my operator was Hermitian, so the eigenvalue is real. Here I obtain a real. The complex conjugate is the same, gives me epsilon. So this is, we have seen, if you look at h of k and you take the complex conjugate, you are going to obtain h of minus k. If you look at the form of this operator. And therefore here you have an equation, state equation for minus h of minus k. And these are the eigenstate with eigenvalue epsilon of k. So you find from here that the eigenvalue for the h of minus k is epsilon of k. So epsilon of minus k is equal to epsilon of k. And the eigenstate u of minus k is equal to the complex conjugate of u of k. Okay? So this means that the spectrum has to be symmetric when k goes to minus k. So the band structure has a symmetry that is with respect to the origin. Right. And this has a consequence that actually at the border of the Brien zone, if the bands are non-degenerate, they have to be flat. So another consequence or property is that if one has non-degenerate bands, they must be flat. That is vanishing slopes, zero slope. At the Brien zone edge. This comes from periodicity and symmetry. That is, if I have a band structure like this, and this is the Brien zone edge. If I have a slope that is non-zero for a band that is non-degenerate, so if my band is going like this, by periodicity, on the other side here, I must have my band going like this, and this is incompatible with being symmetric. Epsilon of k is equal to epsilon of minus k. So if I have non-degenerate band, they must be flat at the Brillouin zone edge. This is the only way I can have both periodicity and symmetry epsilon of k is equal to epsilon of minus k. So this non-zero slope, this is incompatible with epsilon of minus k is equal to epsilon of k because epsilon of k must be symmetric. About the origin. Okay, so there are three consequences. The band structure is periodic in reciprocal space. The band structure is symmetric, epsilon k of minus k is equal to epsilon k. And at the zone edges, if the band is non-degenerate, it must be flat. These are three properties of the band structure. Okay? So I will finish here. Any question?